Okay, I think it's time to start. Okay, couple of topics to discuss. I was looking at, I'm trying to make sure that I have all of my class notes, that whatever I put together and I cover in class, to have it on Canvas. And also I will try to have to add as many examples as I can. I have available from previous classes too. Not that we are going to cover everything in class. We don't have that much time, but I'm going to make them available with their solutions so you can practice if you want. While I was doing that, I found now that there was a class from February 13 where I had that example. All right. So the reason I'm saying that, and we talked about how the charge is distributed here. The reason I'm saying this is because a lot of people expressed concern that we did not have exactly talked about this topic. So I just, the reason I don't take anything personally, to tell you the truth. I'd rather do whatever I can to help. But the reason I'm saying that is, please, when you review either for an exam or whether you review for homework, go back to my notes. I will never ask you to do something that we have not discussed in class. All right. And as a matter of fact, there are many more examples like this that we have. But I just saw that and I thought in the beginning, I had even forgotten about this. And I thought, well, is that something that I discussed after the exam or before the exam? But it was from February 13. Okay, as you can see here, the date goes automatically. So that is number one. Number two, a lot of students who got very good grades asked me whether they should submit the homework. And I said, yes. The grades, I said last time, the grades that and I'm saying that in general because I don't want to send an email to everybody individually. The grades that I gave were reflected only the correctness of the approach. I did not check in detail whether the final solution or the results, the value, for example, or the units were correct. All right, so I only corrected the approach. So if you don't, of course, I cannot force anybody to do anything, but if you do not do this homework extensively, and I don't have this document to grade, then I will go back and regrade your meter. I will have to do it, all right? Because that will be the only evidence that I will have in terms of doing it thoroughly. So my advice is please submit that to all of the solutions correctly. It's a very similar problem. I have the solution 4 already incorporated. Please look at that, because somebody reminded me that I did not have the solution 4. And for the fourth part of the question. And so that is in there. And please do as good of a job as you can, because it takes 250 points, which I'm going to average for your meter. Okay, so that is the last, the second to the last. The last one, I have sent emails to students who did below 100 to come and see me. Not because I want to chastise anybody. It's just I want to see, to help. Is it like something in the class? Is it something that I'm missing, that I need to do something more of X, Y, and Z? And encourage students to come to class and then make sure that they read the material over time instead of accumulating it. A lot of students have come and I want to thank them for that. Many students have not even responded. The only thing that I have to say is that if I don't get a response from these students within this week, and today is the last time to have office hours, then I'm going to think of a penalty. It's going to be in terms of points. I'm going to eliminate some points from the meter. Because when when you ask me for something, I try all the time, especially if you are specific in your question, I always try to come back to you, and you are 200 students and I am one. When I ask one student to come and see me, I don't do it just, it's serious. And for a student to ignore that, I don't know what it means. So, in any case, I would like with that, and I hope that yes, to mention that I would like the rest of the students to see me. Maybe, I don't know whether they're here to hear me either. So, but if you know of anybody who is in that group and who, for one or another reason, I'm not going to yell at anybody. I'm not asking them to come and explain to me why they did not do it. I'm just trying to figure out, first of all, to meet students. Yes. Do you want everyone? No, only the students who have received an email from me. Okay. I send students individual emails. If I had given a blanket email, I would not say that. But if, say, for example, if my department head sends me an email and say, Linda wants to see you, do you think I'm not going to respond? I will respond. I will go the same day if I could. All right. So the fact that the students have not responded does concern me. Okay. That's it for the time being from my end. And anything before we start with magnetostatics? Okay. Magnetostatics. Now, both in electrostatics and magnetostatics, they are topics that you have seen before. And what excuse me, here, let me go back 1 second. What we are doing in this class is to review the fundamentals that you have seen, and then take and use these fundamentals to things that are important to you, important to circuits, and important to things that you will see later, to your understanding of how things work in electrical engineering. Okay, so the most important, if you think about electrostatics, at least, it is always true that electrostatics as a topic is so broad, and magnetostatics too, and electromagnetics, and there are so many applications. So there is no way that within one semester we can cover all of the possible applications. So I decided, at least when I teach the class, to cover applications that I feel you have seen in circuits, so we can connect with this material, or you have seen before, but not applications that may be higher level. So I'm not going to, for example, do very extensive, I will do a little bit of plane waves, because obviously you need to have those for 400 level class, but I'm not going to talk extensively about antennas, because you can see them later. I'm not going to talk about scattering, for example, you can see them later. I'm not going to talk about radars or any specific thing, which is fundamental, because these are things you can always see later. However, I'm going to talk about circuits, because this is so fundamental to electrical engineering, all right? And you have seen circuits before. So from the circuits, what are the two specific components that are so important? Do you know how many fundamental components we have in circuits? Fundamental components. Exclude sources. The most fundamental ones. How many do we have? Resistors, capacitors, inductors. Is there a fourth one? That's for your own information. Diode is not. It's an active, right? Needs a lot of those things to work. Yeah, I mean, it is a transistor, right? So this other one we call them passives. So in terms of passives, which don't cover transistors and stuff, you have seen resistors, you have seen capacitors, you have seen inductors. There is one more element that had been, which people made and used, and they called it a memoristor. We have not heard about that, most probably you're going to see it because it's part of what we call emergent memories. They're using it instead of resistive memories, they're using that. It's a very interesting element. It's passive, but it's not linear. It's not like a resistor. right? It has linear area, but it was discovered about 10 years ago. And as a matter of fact, from the faculty member who is here now in semi-retired, Professor Williams, who was at Hewlett Packard for many years. It was discovered at Hewlett Packard that there was a person who had theoretically predicted it 30 years ago, but nobody was able to prove experimental evidence. So there are really 4 passive fundamental elements. But anyways, for us in this class, or in your undergraduate studies, resistors, capacitors, inductors. Now, resistors are the simplest ones. You have seen them before. You have a conducting element, all right? Inside, there are free electrons because it's conducting. They are going through the resistor. They don't go on the surface because it's conducting, but it's not a perfect conductor. Conductors, good conductors, they have not perfect conductors. They allow an electric field, the resistive elements, for example, which are out of conducting material. They allow an electric field to exist inside the conductor. In perfect conductors, there is 0 electric field inside, all right? So if you want to make a resistor, you don't take a perfect conductor to make it. You take a bad conductor. It has some kind of it has free electrons, but there are not that many. So they allow a current to flow through, obviously, because the electrons under an electric field that will all go around a particular direction, they will flow. So it allows the electrons to go, right? But at the same time, because it has free electrons, and because those go randomly around, and then they lose energy whenever they come in close proximity, all right? It's like you have a collision. They don't collide exactly because they're energy particles, all right? So, but when they come together, it's like think of 2 cars as they collide, they lose a lot of energy, all right? In fact, a lot of this energy goes into the body of the car, that's why it's becoming totally squished. So, and that's what then becomes atomic loss in resistors. So resistors play that role. You have seen them, there's nothing more to it, right? But with capacitors are extremely interesting elements because they hold charge and they release it. They hold and they release it. And this is an extremely important component in anything we do in circuits, including active devices. There is no active device that can perform without having a capacitor in there. Inductors are equally important. Less so than capacitors. You don't find them in digital applications as much, but they tend to be long. They tend to be bigger. In digital applications, primarily you find capacitors. Inductors, however, are important when you do resonance circuits. Why is that? A capacitor stores electric energy, and then only whenever you choose, it will release it. All right? And if you have a switch, for example, you will hold it. Now, inductors are elements we will see that store magnetic energy. So if you have a capacitor and an inductor, but not a resistor, usually capacitors discharge through a resistor, if you have seen. Okay, so you need to have a resistor connected capacitor, otherwise the charge has no place to go. So it will discharge through a resistor. But if you have a capacitor connected with an inductor, what happens is the inductor is a coil, all right? So the charges of the capacitor will discharge through the inductor, and in the process, as they move through the inductor, they become a current. And in the process of doing that, they create a magnetic field. So what happens then if the set of L and C is totally closed? Then charges go from the capacitor. Let's assume you start with a charged capacitor, connect an inductor. Then charges at one particular frequency, charges will go from the capacitor through the inductor, back to the capacitor, through the inductor, and therefore it's going to be this oscillatory behavior where electric energy, as we say, is moving, is changing from electric energy in the capacitor to magnetic energy in the inductor. and that is called a resonance. And they're extremely important capacitors and inductors. They are extremely important in structures that have that capacity to resonate. Now, resonance structures are also very important for active elements. All right, they are very important for filtering. They are very important for mixing. I mean, everything, for local oscillators. I mean, we use them everywhere. So instead of just doing a lot of those things, what this class is going to do is to, first of all, look at the capacitor and try to understand how a capacitor is, how it works. Then look at an inductor and try to understand how an inductor works. And then put the two together and try to see what kind of other functions we can perform. If you have capacitors, multiple, alternating with inductors, and if you do it the right way, then practically you have the equivalent of a transmission line. Not that we make them like that, but in reality, the capacitors in a series of capacitors, inductors, and so forth, can make you transmission line, can make you filter, can make you all kinds of different things that you can do, right? So inductors are extremely important, and that's what we are gonna do in this class. We're not gonna really do everything that you could do in magnetostatics, and there are some interesting things, but we are gonna start with inductors and the inductance, and then we'll go to transmission lines. Okay. So, magnetostatics, things that you have seen. When, let me start with electrostatics because it's very important as we think of magnetostatics to think that in terms of the things that we have already seen. You remember what I said? A lot of times we don't learn in isolation. We learn by correlating new knowledge with old one. That's how we remember it, all right? That's how memory works. Our memory is not like a computer, you put a bit there and then you turn it off and stays. Our memory is dynamic. You correlate something with something else, then you know, and then you remember it. You don't correlate it with anything, and then the human brain, it will erase it. It's not gonna be anywhere to be found. Okay, so with that in mind, you remember what we said. If you have a charge, practically, if you have one charge here, Q, and then you have another charge here, let's say Q1, and then Q2. Each one of these charges, let's assume that both of them were separated. One was here, the other was in another room. We know now from electrostatics that each charge is going to create around it an electrostatic field, all right? It's like every mass creates around it a field, all right? Which in fact is what is called that? Just I forgot about it. But in any case, every mass is creating a field, all right? The same thing, and then you have gravity, so it's creating a gravitational field, and then you have two masses that come together. And then when two masses come together, and the gravity of the gravity fields is impacted by the presence of the other, then the two masses feel a force, which we call gravity, right? So if a charge creates an electrostatic field and it's away from another charge like here, nothing is going to happen between them if the distance is very large. However, if I bring these two charges closer, and then if they're both positive, each of their electric fields that is going to look like this is going to see each other. All right. And the moment they start feeling the presence of each other, then the two charges are going to start feeling the presence of a force. And that force is what is expressed by this equation, where Q1 is this charge, one of the charges, and E2 is the electric field that is produced by the other charge. All right. Now, if instead of stationary charges, we have moving charges, all right? Let's assume that we have a charge Q1 here. Sorry. Yeah. So Q1, but it's moving with a velocity V, and that's charge Q1. And then you have another charge, Q2, that is moving with a velocity V2. So velocities are vectors, all right? Then each one of these charges generates around it a magnetostatic field because of their motion. It's the motion of the charge that is responsible for the electrostatic field, and the magnetostatic field. And when you bring these two charges close enough, and then they see, and so they're moving, let's say this one moves like this, and this one moves like this somehow. If they see each other's magnetostatic fields, then they will feel a force, these moving charges. And that is called the magnetostatic force, Q1 and B2. And as a matter of fact, it's going to be the force that is going to be felt by these two charges here. All right, these two. As opposed to the force that is felt by these two charges up there, stationary charges. Now, when you have a charge that is moving, all right, or is moving within an electrostatic field, and you have other charges that are also moving, and then create, therefore, a magnetostatic field. So assume that you have a charge inside an electrostatic and inside the magnetostatic field. The two fields will not see each other. They will not, the two fields, all right, will not see each other's presence. They are disconnected for electrostatics. When the two fields become connected is when you have high frequency in electromagnetics. But for electrostatics, they are independent. And that's why you can, super important, all right? But in electromagnetics, they are connected. So in electrostatics, if you have a charge that is inside an electrostatic field, and together with that electrostatic field, you have a magnetostatic field, all right? So E and B coexist, but they don't see each other, they just are there. Then that charge, that is, let's assume that you have an electric field that goes like that. This is all made up now. I'm not going to tell you what kind of forces and charge is going to create it. Let's assume that you have an electric field that goes like this, E. And the magnetic field is going to go how? Enclosed. Electric field does not need to close its lines. The electric field, electrostatic, starts on a charge and ends on a charge. From what you have, you remember in magnetostatics, the magnetic fields close the loops, all right? They close loops. So if I have a magnetic field then that goes like this, that is produced, all right? And I somehow have all of this. That is produced by another charge, moving charge, then n charge that is moving inside these two fields, like this charge Q. I always make it like this charge Q that is moving with a velocity V. Then this charge is going to feel two separate types of forces. One from the electrostatic field and one from the magnetostatic. We'll feel both forces because it's a charge, but it's going to only feel this one if it's moving. See what I'm saying? It's going to always feel the electrostatic force. but it will only see the magnetostatic force if it's moving. And therefore, a charge like this here is gonna see a total force, which is called the Lorentz force, which is QE plus QV cross B, where this is E and the green lines indicate B. Okay, so you remember that, all right? These are things that you have already seen. So now, let's show a few applications of one versus the other. Let's see what happens, all right, where you have, first of all, this is the right-hand rule. I have those, my notes. You need to remember that because this is the best way to find this cross product, the curl. All right, let's assume we don't have an electrostatic field. So capital E is not there. We only have B, and B, which you see here, is produced by a current that I have not indicated where it is. Somewhere. The current is, but I don't show it. So I only show a magnetostatic field that has been generated. And then in there, I have a string of metal, all right? So a current can flow through. That is connected to two, somehow it's held in position. These are the two things that's what they indicate rather. All right, so if there is no, this is a string, metallic conductor. If there is no current that flows through this string, nothing happens, all right? I can turn on this magnetic field that is generated by a current somewhere, not here, don't see that. I can turn it on, I can turn it off, and nothing is gonna happen to this one. However, the moment I have a current that flows through the string, all right? This current here is going to produce its own magnetostatic field. And because it's going to be in the presence of the other magnetostatic field, then what is going to happen? That current is going to feel a force. And the current, of course, is electrons, not the electrons. They will feel a force so strong that will move the string if the string is flexible enough. And as a matter of fact, how you find the direction of the force, that's where you have to use the right-hand rule. Why? Because the force here, F, it's a magnetic force, is going to be the current I cross B. Okay? For this case. So the moment the force applies, it's going to see that the moment the string deforms, it's going to see this force. I is the current that flows through. B is the magnetic field that I have generated. So to find the direction of this force, which is a vector, because the cross product between two vectors is a vector, you really have to use the right-hand rule, which means it's like this, always going counterclockwise, all right, with your right hand. And then for me, the way I did it is, sorry, I have my thumb is the current. My other finger is the magnetic field, which goes which direction when there is an X, it goes into the screen, all right? It goes into the wall. So it goes by this. And then by the index, the direction of my index finger. And then the third one is the direction of the force, and it goes like this. And therefore, if the string is flexible enough, then the force is strong enough to deform it. Now, if the current goes the opposite direction, and therefore you use the same hand, then you see the force. So thumb here, index, and the other finger will show the direction of the force. which now goes the opposite direction. So if you want to find, there are two ways for the Henry rule, you will see. One is this, and the other is when we will find the direction of a magnetic field from a current. Okay, but this one, to be able to find the directions here, you have to use, especially, we do that always whenever we have a cross product. Remember that, all right? Okay, now, since we know that we have, when we have a current inside the magnetic field that has been generated by another current, then according to what we've seen before, all right, if the current is constant and has, like the other one I showed up here, like this, eventually all the current has to run on a closed path. Why is it here we don't show the closed path in this one? Because here is one side of the path and eventually comes to close from another side we don't see, but all paths are closed for a current. That is not true for the charges. The charges can be on the two sides of a capacitor. The charges can be on the two sides of a battery, all right, in the two terminals. They don't need a closed path, but currents do. So if we have now this closed path for the one current, I, but then we have another current which you don't see, but we see the magnetic field B that is producing. Then this current I in the small loop will feel this force. And we integrate because, of course, it's like the current that it goes around this loop. So only if I were to take a very small section of this current, DI, a very small section, like a differential, all right, which means that it's very small around one point, then practically this small section of the current feels this small force that is the cross product between this small section and B. So if I take all of these small sections of the current, then practically each one of them is going to contribute to this force. And therefore, if I integrate, and you see close integral here because it goes around this path, then practically I get the total force that applies on this current. Now, what is characteristic of currents? That as they go on their path, they have the same value, all right? Because it's the same number of charges that is moving. What is different on this path is not the value of the current, but its direction. The direction is different as you integrate. And that's why you see this dl with a vector that indicates the direction of this current. And is inside the integral and is the cross product with B. So, because of that, you remember what I said? I said that if you have a current, you create a magnetostatic field. If you have two currents, then you create a force. All right, you need two currents for a force. You need two charges for a force. One charge creates an electrostatic field, two charges feel a force. One electrostatic current creates a magnetostatic field, two electrostatic currents feel a force. Okay, that's how it goes. So, having said that, now we go back and say, now, if I need to have two magnetostatic fields that interact for me to register a force, then I would like to know how to find the magnetostatic field from a static current, all right? And that is the relationship that gives the electrostatic field from a differential, from a small section of a current, all right? That's why you see it. If you integrate around the whole current, then practically you get, as you can see here from the second equation, you get the total magnetostatic field. Now, when we look at this, it starts reminding us, first of all, this is called the Biot-Savart equation or relation, if you remember it from physics. And there was a similar one we got in electrostatics that was called the Coulomb law, all right? So what we start observing in electrostatics and magnetostatics is there are similarities between the two. They are not identical. The relationships are very similar. And that's why we say that electrostatics and magnetostatics have duality. Duality means the two phenomena are different. They have different sources. They express themselves in different ways, but the laws that govern them look very similar. That's duality, all right? And there is duality between electric and magnetic fields. And then you see it first of all in electrostatics. Before we go to see that duality, I wanted to say that there is a difference in how we talk about sources and about density. All right, so let me spend a little more time on this. And you're going to see it here. But let me remind you from electrostatics. In electrostatics, we talked about a point charge. Okay, Q. In magnetostatics, so that was a point charge. And the units are always coulombs. And then we had the situation where we have a charge distributed instead of being at the one point, that is ideal, all right, to have a charge at one point. In real life, we have charges distributed. The moment a charge distributes, then you have to define a charge density. And you remember we said that we had a line charge, all right, so line. And the line charge density was coulombs per unit length, say per meter. Then we had a surface, okay, S. And on this surface, the charge density, which was called the surface charge density, was coulombs per meter square. And then we had a volume, V, okay, so here the surface. And volume V, where the charge was distributed in a volume, and we called it QV, and it was coulombs per meter cube. So that happens in electrostatics. Now, magnetostatics, there are other things. In a way, you have a charge, but it's moving. So the charge creates a current. And as a matter of fact, this current is going to probably close someplace. All right, so that is a loop. And let's assume that the current goes like that. And it's I. So what is that? Is the same charge, Q, moving with a velocity V, but it's moving along this particular loop. And therefore, this current has a direction that changes with position. All right. That, even if it has the same meaning, so let me take it back. The dual concept, therefore, of a point charge where everything is located at one point is a current like this, where the charge is a point charge, but it's running with a velocity, is moving with a velocity V and eventually creates this current. All right? And therefore, this is measured in amperes. So this one is in amperes. Now, that therefore is the equivalent of the point charge. All right, so I will take it a little higher. So this is, let me see, I'll put here 1, 2, 3, and 4. And then here, 1 is this one. And it's up here. Now, if I were to cut a piece of this wire, all right, let's assume that I cut it someplace here. what would I see here? I would practically, the cross section is going to be 1 point. All right, that's why that corresponds to point charge. However, in reality, nothing is 1 point. There is no one line. There are no wires that look like a line. These are all wires, but they have a particular geometry. All right, so practically what that tells me is that if in reality this wire, which is here, this wire, if I were to cut it, it would look like this. For example, and then it's gonna close somewhere. All right, so it has a particular cross section. And if I were to look at the cross section of this wire, so the current will flow in a group of line currents. So it's almost like this. All right, so there will be a lot of charges that will move at the same velocity. And this one is called, the one is called surface current. And the charge density for that is a surface current density, all right? And is measured into amps per surface square. Because to find the total current, you have to take that and multiply. There is no equivalent to a line charge. It's only this line that it looks is called surface charge. And, or in fact, some people, because it corresponds, some people, because some books, in fact, because it corresponds to this, they will call it a line charge. But in reality, you have to multiply this area, because here it's a circle, and then with an area. Now, what is the case of a, so that in fact is equivalent to 3. Okay. So 3. Let me say here 3, because in reality, that's what it is. Is a surface charge. Excuse me, surface current. All right. Now, do we have volume current? Do we have volume current? What do you think? No, we don't have a volume current because the current goes in single filaments. All right, this is a filament. Filament is something very thin, thin line, filament. This one is a collection of filaments. The current, every charge, because you think that of the current as made up out of multiple charges. Every charge runs, all right, with the same velocity, like electron. Every electron will run with the same velocity. They are not going to get together with other electrons because there is a distance from one electron to another due to repulsive electrostatic forces. So the electrons are not going like this. They don't come together and then fall apart. No, the electrons will start like this. They're going to be contained within an area, which is the wire, and each electron is going to take its own path. They're not going to cross paths. Period. They're going to only cross paths by force because the structure of the material is like that, and every time 2 electrons cross paths, they lose energy. All right? If there is a material where the electrons, as they move, they are forced by impurities. They are forced to cross paths, really cross, not at distance, cross paths to hit each other. They lose energy. So that's very lossy. So in good wires, every electron goes on its own. Therefore, it does not make sense here to say anything else but that this is a collection of filaments. And to find the total number, you have to develop to define this current density and multiply by the area. But there is no volume then current density because every charge creates a line. Right? There is no volume. like a charge. So we don't have volume current densities, no. Volume current density does not exist. Now, does not exist. Do we have a line current density? Only theoretically. And when does this happen? Okay, let's assume that I have a conductor, like a thin conductor, but it's like in microelectronics, all right? And it's on top of a metal. This is called a microstrip, and it is, it is a line that connects all of the digital circuits and so forth. You can see them in microelectronics. Now, the current flows here. Let's assume that the current flows like that, all right? So, however, there's a ground here. The electrons that run here, this create this current, will do what? Will be attracted, the other electrons here in the ground, they're gonna force themselves to leave, which means that underneath here will be positive poles. That is not gonna change because it's physics. All right, electrostatic forces between charges exist even when the charges move. So there are going to be positive charges here, and all of the electrons are going to come to the lower surface. And that's what happens really in microelectronics. All of the current flows in the lower surface of a conductor that looks like this. And those conductors, in fact, they look long. They're long lines like that, all right, in 3D over ground. So this current here can be assumed to be only flowing in the lower surface. And therefore, because they flow in the lower surface, you can assume, as here in my notes, that the whole current flows only on one thin surface. It's a bad drawing here. I will redo this, but it's only along a surface. And therefore, you can call that a line current density. And why it is a line current density? Because to find the total current, you have to multiply with the length L of this, flat line. So that's a current line density, all right? It is in amps per meter. So this is important to remember for the units, all right, as we will look at different applications. But now you can see a little bit how things here correspond to each other. And then what we're going to do next time, we're going to start to remember the fundamental formula. You have seen all of these formulas in electrostatics and magnetostatics, but what we would like to do is to look at the duality. So for example, this and this, QE and QV cross V, they are dual. Coulomb's law and Biot-Savart law, dual. They have a cross product here, but look, the 1 over R squared. So there are specific characteristics in both in electrostatics and magnetostatics about how the fields bend away from the source. It will be the same. But the difference will be on what is the direction of the electric field, what is the direction of the magnetic field, all right? So we'll start with this next time, and then we are going to start looking at what, this is a loop, a wire loop. We'll start looking at what kind of fields, magnetostatic fields, a wire loop is creating. Why do we look at wire loops? Because we create inductors. Right? So loops can be wire or can be rectangular. All right, with this, we'll continue on Friday. Thank you.
Question.
Yes.
So on one of the solutions, specifically 2B, right here. So I was wondering why you have the 2.
The 2 because half of the lines go up.
Okay.
and half of the lines will go down.
Okay. But like,
So what is gonna be excited down here is gonna be the equivalent of half of this chart.
but oh, I see. Yeah, yeah, I see. Okay. So that's why here it's just the regular form of Q over A.
Yes.
Okay. Thank you.